Good evening. In this video we try to solve a problem of CDC interface for the pulse sampling. Let's say the problem definition look like as 100 megahertz is a one clock domain and second is a 10 megahertz clock domain, and we want to sample a pulse from the 100 mega to 10 mega. The pulse width, it is about 10 nanosecond. It is a one clock period of the 100 mega. So for the brief, I just explain in paint. Let's say there is a two circuitry are there, 100 mega and 10 mega domain, and there is a connection between these two, and we need to detect the pulse from the 100 mega within the 10 mega. The duration of the pulse is 10 nanosecond, as it is one clock period of 100 mega, and corresponding one clock period for 10 mega equals to 100 nanosecond. So how we can do it? So logically we cannot sample these tiny pulses. For sake of explanation or to view what size it look like to be. So in this diagram, the upper one clock is 100 mega, and this is a pulse. This is a 100 mega waveform as illustrated. It is a pulse we need to detect at in 10 mega area. So how can we do it actually? Because the pulse nanosecond. So how we can detect this 10 nano using how we can sample this pulse using the 10 mega. So the logic is directly we cannot do it, but if we try to extend this pulse equals to up to the 100 nano or more than that. So logically we can extend or stretch this pulse, tiny pulse of 10 nanosecond to the clock period 1.5 times. Let's say it is a 100 nano and this is a 50 nano additional. So 1.5 times if we stretch times to the clock period of the receiving domain, then we can able to get that pulse. Okay, so the logic is very simple. We have to stretch this pulse up to the 1.5 times the clock period of the receiving domain. In this case it will be the 150 nanosecond. So in any case it will detect this pulse. So the code for this in Verilog, I hope you got the problem. We need to sample the pulse of 10 nano. So to sample the 10 nanosecond pulse in 10 megahertz domain, we need to stretch the pulse for 10 megahertz. That will be 1.5 times to the clock period. That will be equal to about 150 nanosecond for the safe side. So I designed a code where it will check the logical one on this pulse input pin, and it will increase the counter of almost 15 cycles, and then it will release that. So this duration is almost 150. So here the simple code is there where I use a counter to check that. For this first it will check the pulse pin is 1 or not. If it is 1, we load the counter with the 15, and it will gradually decrement that counter up to the 0. So once it is get 0, so output, we make the output equal to 0. So the test bench is a very simple one. So at this moment we we send a pulse of 10 nano and wait for 200, then again we send one more pulse of 10 nano. So, and what happened? In this example, we are trying for the only 10 megahertz, maybe 12 or 8, like that. So, in spite of counting up to the fixed value for the 15, so we make arrangement to have this value dynamically at the input way, okay, so that this model can be applicable for the various range of the destination clock domain. So for that I just add one pulse width value. We can alter either 15, 19, like that. So with the help of that counter check value, we can extend the pulse of output, so that we can use this concept for the different clock domain, for the values of the clock domains. So if you check earlier code and this code, only the change is that we add one input bus for the pulse width, and through that we can provide the what desired width we required. It depends obviously on the destination clock domain value. The rest of the thing is same. This is Testbench for the same. Additionally, we put the counter values. Here we put the 15, here we put the 25, like that. So after simulation, we got this is a pulse of 1 clock period of, that is 10 nano, and for this 15 we stretch that pulse to the 15 clocks, okay. The cause of that is that if this width, even though it is a little bit before or after, still we get one of the rising edge of the destination clock, okay. In this case it reflects that it will catch up the 2 clocks, so we get the pulse here. Also from this pulse we get this stretch pulse, okay, and also we can have the corresponding output sample pulse, okay. So sometime what happened, the alignment of this 100 mega and 10 mega is not properly aligned, so sometime it missed the rising edge. So still the width of this is we set already as 1.5 times. So in any case it will obviously within the one of the rising edge of the destination clock. So in that case we pick these things and it will reflect on the output pulse. So we keep the one 2 flops synchronizer as we see in this code, okay. I check that. This is a code where I put 2 flop synchronizer for the output, so that it properly aligned with the terminology of the sampling at the destination for the mitigating the metastability. And please ignore this asynchronous reset, as it is only demonstration, so it's not bother about much, okay. So while designing you always prefer the synchronous reset, okay. So I hope this video finds it helpful to you. If any comment or anything like that, you can post it below, and please subscribe my channel, make comment and hit like button. Thank you.